And the record is on. Okay, guys, can you see properly what I am sharing you? Yeah, okay. Just give me 1 second. Okay, guys, so as I said before, this lecture is mainly aimed to the explanation of the software Telaio 2D. Okay. So this software, the meaning of the software is frame, basically in English. What is the logic of any software used for structural design? We start with a structure with a specifying the geometry of the structure, the nature and the geometry of the elements which provide the structural resistance, and the loads that are applied on the structure. You have seen it several times idealizing the structures in plane frame, okay? And each element is, for what you've seen so far, just a line. We have seen restraints, you have seen loads, and so on. Loads can be both forces or couples of forces, so moments. And what you've done so far is you get a structure with a geometry and a load condition already explained, and you have to study how the forces tend to get into the structures. What is the flux of forces? How they are transferred to the ground in terms of restraint constraints reactions. Okay, and then you find how they are distributed inside the structure, studying the distribution of internal forces. So shear force, axial force, and bending moments. Okay, the outline of this lecture is here represented. First of all, a very, very quick background on structural mechanics. Then we will see why this is necessary. It is useful because with softwares we can do. I see there is somebody who is struggling with the internet connection. I am very sorry for them, but the record is on and I will upload it within the weekend. So,
Professor, I'm sorry. We can see your screen only the left half. The other half is like black. Is it on purpose?
Yeah, actually, yes, because I'm keeping WebEx on one half of the screen and the other part is the slide. Is it a problem for you? You can see it small. You want it? You want it?
It's a little small, but okay. Okay. Now it's...
Okay.
Thank you.
Thank you. So, as I was saying, we can solve structures or by hand or with the help, with the aid of software. And the problem is that software is very powerful and we just cannot always manage to control it. So we have always to check its behavior. So that's why I will do a little bit of background in order to establish the how to control the software. So we know how a structure behaves. We don't know how to solve a structure looking at it and just snap it. It takes time, and so that's why we use software. But we also need to have tools to control what the software is actually doing, and this tool is basically our experience on solving structures. If we see a hinge, we know that there we do not expect any bending moment, basically. Okay. If we see a free end with no load applied, for example, in Italian, una mensola a sbalzo, with a cantilever. Okay, if we have no load applied at the end of the cantilever, we expect 0 shear force, 0 axial force, 0 bending moment there. Okay, because there is nothing that can provide those forces. And typically, if we have some deformation, some motion that is prevented by some restraint, there we expect to have some reaction force, and so some internal forces. Then the example that we will see are related to one span beam. So a very simple case, just to check the work of the software. Then we will briefly return to flexibility coefficient and try to maybe understand from a different viewpoint what they are and how to compute them. Then we will solve a free-hinged arch. Finally, not finally. Furthermore, we have a plane frame, and we will use this software in order to start doing some consideration on the structural behavior of frames that so far we have not yet seen so much. And finally, continuous beams, in this case, free span beam. So one continuous beam with a generic distribution of load with different length of the spans. So typically this could be a beam on several columns, or it could be a bridge. Okay, we have the deck, free spans, and when we compute the bridge computation, we need to consider a different distribution of forces on the different spans in order to maximize, for example, an internal force. Okay, let's start from the scratch. We are dealing with structural dynamics, let's say, or structural mechanics. What do we need to perform the numerical modeling of the structures using softwares, but not only using softwares, using whatever tool we have, even when we do hand computation? First of all, we have to know the geometry, okay? So we have to have clear which are the structural elements of the structure, where are them, so how they are connected one to each other, and finally, how they are actually made. Because so far we have seen just that a beam is a line, a column is a line. Everything is in as only one dimension. Okay. In the reality, this is not the case, obviously. Elements have a volume, have an inertia, a mass that is associated, and a material. It can be steel, it can be reinforced concrete, it can be wood, it can be stone, masonry. And we have also seen that according to the geometry, talking only about the geometry, each cross-section of a beam, for example, is associated to an inertia, so a moment of an inertial moment. The more, the higher is the inertial moment, the stiffer is the element. Similarly, if we deal on the materials that compose the elements, we can see that in our computation we have seen a lot of time the coefficient, the Young's modulus, which is the letter E, and the stiffer is the material, the higher is the Young's modulus, and the stiffer is the structural element we have in our structure. Then we have restraints, because elements do not just fly around, but they are connected to each other. Okay, we know that beams are connected to walls and to columns. Columns are connected to each other and to other beams. Because all the elements are then connected to the ground somehow with the foundations, and we have to know what kind of restraints do we have. What does it mean? That's trivial. If the restraint provides the possibility to have any kind of motion or prevents any kind of motion. So if we have hinges, if we have vertical supports, if we have full restraints, or what. And then the loads. How can we model and idealize the loads? We have distributed loads, we have concentrated loads, and so on. So let's start from the first example. We have a one-span beam. Okay, so we have just a span with a beam that is completely restrained on the left-hand side and is simply supported on the vertical on the right-hand side. A load is a concentrated load is applied in the midspan, so perfectly at 1/2 of the beam. We have 3 degrees of restraint because we have only one element, and then we have 3 plus 1 degrees of restraint. Sorry, before I was saying 3 degrees of freedom, obviously, and 4 degrees of restraint. So the structure is statically redundant. We cannot solve it using only equilibrium equation because we have one missing unknown. We can use force method, we can use the elastic line, we can use a set of other tools, but we have seen so far only these two. What we usually do in this case is just turn this clamped-in section, the first one, into a hinge. In this case, I have plot the plot of a roller. Okay, this is theoretically a mistake, but practically it is fine because the difference between the vertical support and the hinge is just that the hinge prevents also the possibility to have a horizontal displacement in this point. But we know that if we have no horizontal forces, the structure will not tend to go anywhere horizontally. So we are just spending one freedom one equilibrium equation, that is the horizontal displacement. We just say we don't use that equation, but we know that the associated horizontal reaction in this point is 0. So we get rid of 1 degree of freedom and 1 degree of restraint. In Italian, it is what is called l'abilità non sfruttata. If we want to solve this structure using force method, I don't want to go into details, just going quickly. We have to exploit the superposition principle. Okay, we consider the effect of only the bending moment and the effect of the vertical force, and then we say that the original rotation in the node A has to be equal to 0. How we exploit that information? Simply summing up the rotation in this point associated to this bending moment and the rotation in this point associated to the external load. Okay, now a question for you all. Do you think that the deformed shapes are consistent with the loads that I have applied? I mean, if I have a vertical force here, do I expect this kind of deformation? Yes, no, why? And if I have a bending moment here, do you expect this deformation? Yes, no, why? If I am asking, maybe there is something wrong.
I think the one associated with the rotation is on the other side of the beam.
Yes, absolutely. Thank you. Also, I saw that someone else said it, because we are applying. We don't know actually the sign that the bending moment will have, but if we assume a counterclockwise bending moment in the node A, the first node, then we have to expect a counterclock rotation in the node A. Instead, here we have that the node A is rotating clockwise. Thank you for your answer. In fact, this is wrong. This is what I expect. And then this is the condition, the compatibility condition, in order to find the values of the redundant unknown. Okay, now that is very trivial. We have the flexibility coefficient here. If we consider only the structure, we know that the vertical supports in A and in B are equal to x over L. This is very trivial. We can use just two equations of equilibrium, which are the two equations of equilibrium that we have left. Then we solve the original structure associated to the external load. We have this flexibility coefficient, which is different and depends on the load. We impose the compatibility equation. So the rotation in node A, VA, is the sum of them both, and has to be equal to 0. So we know the rotation of the first one, we know the rotation of the second one. One is equal minus one, the other. Okay, so we can find the value of the unknown x. That is the only unknown in our problem, which is equal to 3pl over 16. Now, we can write the equation, the structure again, substituting to x its actual value and solve it again. Or we can just say that the reaction in the node A is just the sum of the first one and the second one, where in the first one we have x equal to this stuff. Okay, here there is a problem. I said that we have it is equal to L over x. It's a mistake. It's x over L. I will correct it before uploading. And same for the second one. Okay. Okay, now that was just a reminder. Now let's start with the span beam. Okay. I have to switch laptop. Oh, okay. I can do just one thing because I am working on a computer that is not mine this morning. So we can just take advantage of this. I can download the software. It takes 0 time.
We can see the desktop.
Yeah, I am trying to change the stuff I'm sharing. Okay, can you see now Firefox?
Yes.
Now I have to download them again. This is the software I was talking about. We just download the pacchetto comune, Telaio CD. And then we go at the bottom of the page to download Profili V6. Okay, now it is better if I just share everything. The window, okay, screen. This is what has been downloaded. First of all, we need to extract everything from here. And then we can run this setup. If you have already done this, you can just skip these few minutes of lecture to have a coffee. Can you see still what I am saying? The installation of Pacchetto Comune?
Yes.
Okay, so here we have to click OK. We have to click here on the laptop, on the image of the computer, not here, otherwise we will exit the installation. I know this seems trivial, but several foreign students obviously don't know that, and that's what I will do. Click on the bottom of the page. So we have installed the Pacchetto Comune. Then Profili V6, we extract everything. Pacchetto Comune is just something that we need to have installed on the laptop to run all the other Gelfi softwares. Whereas Profili is it's not actually a software, it's more of a database. And here we say OK, we click here. That's what I say. If you have any problems, please ask me, because several times the problem can be very trivial and you can waste a lot of time simply because you didn't ask. And that's a pity. The installation is complete. Okay. Telaio 2D. This is the actual software. The previous one, Profili, is just a database of all the commercial cross sections that are available for steel elements. So we can see all the HEA, all the IA files. Okay, now also this is done. I can just share it. It is still better if I share the screen, I guess, because a lot of other windows will pop up. And so it is very important for me to print everything, to share anything. If I need any help, I will just check it. Okay, so basically how this software works. I hope that if you had any problems in installing it while I did this, they watched the procedure and maybe they can solve the problems. Otherwise, again, ask me. We can see them during the break. So, if we need to start a new structure, first of all, we have said it several times. The first problem we have to solve is the geometry. So how to define the spatial geometry distribution of the elements. So how we do everything? Okay, first of all, we create a new file. That's what I did before. We have this plot with all these menus, menu view. So we can just change some elements, from some graphical elements. The summary, so the information on the structure we are introducing, global, we have load cases, units, and groups. First of all, check the units. Here we can change the units. Maybe you can have something different. I don't know. It depends. Typically, the length for us is useful if it is in meters. Okay, so when I say that beam 1 starts in 0 and ends in 5, it means that the beam is 5 meters long, which is a length that is expected for a length. Otherwise, I could pick centimeters or millimeters. But in that case, I should say that beam 1 goes from 0 to 500 if I'm working on centimeters. The mass, again, actually we don't deal really with mass because all the weights will be considered in Newton with the forces, not with the mass. So we can stick to tons. Inertia and area are usually it is a good idea to work on centimeters square or centimeters to the power of 4 for the inertia and for the area and the inertia respectively. Otherwise, we can choose millimeters or meters. Now, the stress modulus, which is a very good idea to work in megapascal, because we have seen a lot of times the stress. The stress will still. Okay, no, so far we have only worked about modulus, so the inertia moments, the Young's modulus, for example. Also, when you have seen it with respect to the steel, you have also seen the value in megapascal or gigapascal, okay, because they are very high numbers. Then force, it is a good idea to work with kilonewtons, because the Newton, okay, you know how much is a Newton. If we have 1 kilo of mass, kilogram, since the force is mass times acceleration, the weight of that mass is 10 Newton, because we multiply the mass, which is 1 kilogram, times 10, let's say, meters over square seconds, which is the gravity acceleration. Okay, so all the times we have a mass, the Newton, the weight in Newton, the force in Newton will be 10 times that mass. So it is good to work in kilonewton for our theory. Then temperature is decreased, but we don't care about it, and density in kilograms over cubic meters. Okay. Now let's start with geometry. But this is true for every time. Every time you will see a new software in your life, please always check the units. The units should also, here they are, meters, megapascal, ton, kilonewton, centimeters. Everything is represented here. Newton, no, create, node. Okay, we want to solve check it. Okay. So the first example is that one. Let's go back to the beginning of the presentation, because I have not it. Okay. This one. We have seen it solving by hand, and we have seen that we have to do quite some computation. If I want to solve the same structure using the software, assuming that the length is 5 meters, as I said before, and the weight and the load is 100 kilonewton, obviously downwards. We need to define the nodes. Each element is just a connection of different nodes that we have already defined in the plane. So node 1 is at the beginning, so 0, 0. Okay? Node 2 is this one. We have to define a node every time the geometry changes or every time a load condition is applied. So we have a concentrated load, or we have the beginning or the end of the distributed load, or whatever. So in this case, we need a point in the midspan. We said that the span is 5 meters, so the node 2 will be in 2.5. So we have node 1 and we have node 2. Node 3 will be in meters equal to 5. Okay, so first step, we have created the nodes. Then we create the element. We click create element. We select this. Here it asks us what kind of element we are dealing with. We have just beam 2. I don't know why this 2 appears, but okay. It is something from the software. And it asks us which property has to be associated to this element. So far, this is only important when we are dealing with different kind of elements. So if we have a frame with beams and columns, obviously the beam and the column will not have the same area, okay? Because they are subjected to different kind of load conditions. The beam works in bending and shear, whereas the columns usually works on main axial force, okay, and also bending moment. So we just set to stick to property 1. We click the node 1 and click the node 2. Simply clicking on the nodes, it creates an element. Then we click on node 2 and then we click on node 3. So we have created the element number 1 and the element number 2. They are highlighted in red. Homogeneous elements will be colored with homogeneous colors. If we want to set a new property element, so if we say property number 2, it will be drawn in some other color, but we don't care about it now. So here so far we have the spatial distribution of the elements. Okay. What do we need now? We need restraints. We need to understand how these elements are restrained each to the other and with respect to the external world. Now, I have split the element into 2 elements. So the beam that I had at the beginning is now beam 1 and beam 2. But obviously, not obviously, the software considers different elements which converge into the same point. So in this case, element 1 and element 2, which have in common share the point 2. Here, it is by default fixed. So these 2 elements behave as just a beam. So we don't need to restrain anything here because it's already done in automatic. But we have to impose the external constraints. So let's go back to the example. We see that we have a full restraint at this end and a vertical support in this second one. So attribute node restraint. We select node 1. We want to impose that this point has to have 0 vertical displacement, 0 horizontal one, and 0 rotation. So here we fix what are we restraining. Yes, we are restraining x, we are restraining y, equal to 0, and we are restraining the rotation r, equal to 0 radians. We apply. So here it appears a symbol. This symbol are 3 purple lines. It means that each line is associated to a prevented motion. So the vertical line means that we are preventing the vertical displacement, or maybe we are fixing it, because we can also fix a displacement equal to 0.2 points, 0.2 meters. Okay, so we are fixing a displacement. It can be some foundation settlement, qualche cedimento di fondazione. And similarly, the horizontal line means that we are preventing horizontal displacement. The diagonal one means we are preventing the rotation. In the node 3, we do not have to impose both x, both y, and both r, but what do we have to impose? Any guess? Don't be shy.
The bending moment, R, the rotation.
Well, thanks for replying, but actually, what do we have here, Mohammed? Mohammed Amin? What do we have at this point?
I believe.
Sorry?
A roller. A roller.
Yeah, a roller.
1 degree of restraint. No.
Yeah, restraint. No, but I was asking to Mohammed Amin because he answered it before. But thank you. So you said right. We have a vertical roller. So what does a vertical roller prevent?
The shear force, the vertical movement.
Yes, not the shear force, because the shear force is about the element.
Okay.
Now we are talking about displacement. Okay, and
The
you said
vertical
right.
displacement.
Yeah, as you said before, the vertical displacement. So we have a possibility to have rotation. In fact, in both this configuration, we have an expected rotation when we have any kind of load applied on the structure here. And similarly, we could also have an horizontal displacement if if there were some horizontal force. So in this case, we have to fix only.
Sorry, Professor. Do you know why I don't have the like when I click on the element and I wanna add a beam, I don't have the available properties of the beam.
Yeah. At the beginning, you don't have it, but when you start working, then it appears. But we will see it in 5 minutes.
Okay, thank you.
You're welcome. So when we think about the restraint in the node 3, we have to prevent just the vertical displacement, and we set equal to 0. Apply, and as expected, a vertical purple line appears on node 3. Okay, this is just also a way to check, because sometimes you will mess somehow, and that's physiological.
Hi, Professor. I didn't understand very well. In the first restraint that it was fixed, we cannot have any kind of movement, and on the second restraint, we say that we just can't have the vertical movement, and we can have rolling and the other kind. It's true?
Yes.
Yeah. Thanks.
Yeah, but that's what you can see from. Oh no, what's happening? From here. This symbol means that you have no vertical displacement, no horizontal displacement, no rotation. This is the meaning of the symbol. And the meaning of this symbol is that you have no vertical displacement. So how I translate this information for the code? Just preventing these kind of motions. Then we have the geometry. We have the restraints, we also need, don't worry about all the stuff I'm doing, because then you can see, you will see that there are slides with the key passages about all the things I do. And for this reason, these slides, since they will be sent to you, delivered to you by Professor Gentile, you don't need to take compulsively notes on everything. But if you want, do it. Please work about the why I do things, not what I do. So we have the geometry, we have created the elements, we have imposed the restraints. We need also the loads. So it is an attribute. Okay? Since it is a concentrated load, it is an attribute of the node, not of the element. If we had distributed elements, then it would be an attribute of the beam. And we would go for distributed loads. We will see it later. For now, it is just node. We can impose restraints, we can impose force methods, force moments, or translational mass. We don't care about it. We just go for force method, force moment. Where is the load applied? In the node 2. So we select node 2. What are we applying? Just a vertical force, and we want to apply minus 100 kilonewton. If it was a bending moment, we would go for minus 100 kilonewton meters in the moment. Okay, but this is not the case. We can just unselect what is not of interest for us, or we can take it fixed to 0. It is the same. So I do it in both ways to make you see. We have already selected where the load is applied. Apply. So a big green arrow appears on the node 2, and it is directed downwards. So we are quite happy. So far, our structure is always more like this. If, okay, I can save it. But it is better if I go for save as. Structure, then structure design. Simple. One beam. One span beam. So if we want, we can work on it later, and it could be helpful for you since you have to do it for the homework. So to solve the structure, you only have to click on solve menu, to go on solve menu, and you have possibility to have linear static analysis, linear mapping analysis, second order static analysis, or evaluate the natural frequency or the spectral response, or perform some computation based on the spectral response and on the static forces. But for us, it's just a linear static analysis. You think we need to, and at the end of the analysis, we know the software will provide us the values of the restraints, the reaction forces, where we have restraints, the displacement everywhere. So we know how much is the beam deforming in this node, and this node. We will only have the information on the nodes that we have defined. Okay, so if we want to evaluate the displacement on a mid-span of a simply supported beam with a distributed load, we have to impose node 1 and node 2 at the two ends of the beam, but also the node 3 in the mid-span. We don't really need it because the load is not applied in the mid-span if I said that we have a distributed load, but we can use that node in order to check the displacement in that point. So if I ask you now, are we done? We can run the analysis, or we miss something. We have defined the geometry, we have defined the restraints, we have defined the loads. So basically we know everything about the structure, we know what the reactions will be and how much it deforms. So I could evaluate the displacement of node 2 under the 100 megapascal, 100 kilonewton load applied. Yes, no? There is someone listening? I know that that's not the most exciting thing on the world, but
Seems yes, but I'm not sure.
okay, thank you. Actually, no. We lack only one thing, but thanks for saying, because we didn't say anything on the material properties and on the section properties. Okay, so as much this line could be like a rope, or it could be like a beam of in reinforced concrete with 1 meter's height, and obviously different elements and different geometries or cross sections will behave differently under this load. So the deformed shape will be qualitatively the same, but deeply different in
So, Professor,
yeah.
how we were solving all these problems till this point without
we can just go on property. No, sorry.
Having any properties on, you know, assigning any properties to any beams. We just solve all the problems.
Yes, yes, yes. In fact, this is the last step you need. We go on property. Okay. Property, we can set the properties of materials, of section, and geometry. So basically, material, we can just select. Sorry, I did it too quick. If we go on material, there is a little button here we can toggle. We can select materials, and we have a list of several materials. So several classes of concrete, wood, masonry, steel. Maybe you don't have masonry, maybe I defined it. No, because I haven't installed it right now. So you will have basically everything. And we can select just steel because we want to work on steel structures for now. You have seen just steel. If I select
sorry
steel,
to disrupt. I'm very sorry to disrupt.
No.
We were solving all the problems till this point in our class without assigning any materials to the beams and things like that, and we reached to the diagrams of load distributions, shear force distributions, and things like that. How was that possible? I'm a little bit confused.
No. That's I'm very happy quite because you just set a point which can go and just fly away. But if you think about it, it's quite strange. So far, we have worked only with homogeneous structures. Okay, so we said that all the structures are always the same material. And if you deal with, how to say, homogeneous structures or statically determined structures, the distribution of forces inside the structure and the reaction forces do not depend on the material. Why? Because we ended up, we can just, actually I'm quite mad because that's a tricky point that everybody forgets about, but you're obliging me to talk about it now. Okay. Here, when we solve the compatibility equation in a structure, we have that we impose this rotation plus this rotation equal to 0. Okay? So we have this equation which becomes this stuff. So our unknown is only x, capital X, and so we say that capital X is PL square over 16 iota times 3 times iota over L. Why? Because we had all the materials are the same. So the E in this part of the structure is always the same E that is used. So at the end of the day, the solution does not depend on that parameter. If I had two beams with different materials, then I would have E1 and then E2. Okay, as we have seen last week, that L is not always L. L depends on the length. So if we have a two-span beam with one span long 2L and the second one L, the flexibility coefficients will have 1 L to the power of 2, or better, 2L to the power of 2 sometimes, and so we will have 4 L to the power of 2. Whereas the second beam will only have L. Similarly, also, if we had that the first beam does not have a different length than the other, but a different material or a different cross section, so it has a different E or a different iota, then each flexibility coefficient should be associated to E1 iota 1 or E2 iota 2. Okay, and then we compute, so we don't have only E and iota. We would have E1 and E2 or E3 and so on. And when we combine them all together, they would appear. We would have E1, E2, E3, and they are all known because we know the materials. But we would have all these different terms. And so in this case, if we have unhomogeneous structures, the distribution of forces depends on the stiffness of the material, because they do not simplify here. If the structure is the same, everything just goes away, because we have all the terms with the same iota, 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 iota. We just multiply everything for iota, and everything disappears. Otherwise, we can have some coefficients with E1 iota 1, some coefficients with E2 iota 2. So we can simplify some of them, but we have to take into account of the others. So for structural redundant structures, if the structures are homogeneous, the distribution of force does not depend on the distribution of stiffness. So material and cross-section. If the redundant structures are inhomogeneous, are heterogeneous, then the distribution of forces will depend on the distribution of stiffness. Okay? We can have other examples later on, but it is better to see them with an example. If the structure is statically determined, otherwise, the distribution of forces will never depend on the distribution of stiffness. Why? Because we can only use equilibrium equation. If we use only equilibrium equation, we have no iota appearing, popping up. Okay? So if we have a simply supported beam, okay, like the deck on the bridge, just something that we can, I don't know, a beam to cross a small river, and one person on top of the beam. The deformed shape will be that one. The load will be one half on one support and one half on the other support. Okay, so the distribution of force does never depend on the distribution of stiffness. So on how many materials or how many different materials do we have, or how many different cross sections we have. But the deformations will depend, because if I have one beam in rotten wood, or if I have a beam in stone with the same dimensions, obviously the rotten wood will deform a lot and possibly fail, whereas the stone maybe surely deforms the less, because it's intrinsically stiffer than the wood. Okay. Similarly, in any case, the deformation and the displacement always depend on the distribution of stiffness, because stiffness is how to translate a force into displacement. Okay. So let's go back from the beginning. If I have a statically redundant force, statically determined structure, I have that the distribution of force does never depend on the stiffness distribution, so I can solve the structure, find the reactions, find the internal forces, never wondering what the material is. If I have a statically redundant structure, I should worry only if I have different elements, different stiffness in my problem. If the material is always the same, and if the cross sections are always the same, I can neglect it, because if I also take them into account, they only have the same E and the same iota, and then I can just simplify them when I impose the compatibility equation. Whereas if I want to go and find the displacement, I will surely need to know what is the material properties. But you never did, actually. So so far you never computed the displacement for a statically redundant or statically deformed determined structure. Do you? So far, when dealing with hand computation, you just didn't care about. You only cared about when you had to do it with the elastic line. Okay, and there, if you remember well, in the elastic line, the displacement and the rotation depended on the iota and the Young's modulus. Okay, if I have solved that question, I can go on. Is it clear now?
Very clear. Thanks.
Okay. You're welcome. So far, so we did everything. We can maybe. No, we didn't do anything. We have to set materials. Okay, we say still. If we select still, we see that all the properties pop up here. Material name is still. The Young's modulus is 210,000 megapascal, as you have seen with Professor Gentile a few lectures ago. The Poisson's ratio 0.3. The density is 7,900 basically kilonewton, or 8 tons over square cubic meter. The thermal expansion coefficient is 1. Okay. Then we can define the section, saying which are the area and which is the inertia moment of the cross section. Or if you have downloaded and installed the Profili version 6, the Profili software, you can go on geometry, you find a blank window, you click Profili, and something appears. So here there is the dimensions of, there are the dimensions, the drawing of an IPE80 cross-section. What you cannot see is that another window had appeared, but it's behind. So we magnify it. Even if I magnify it, it is always small. Here in this beam, in this window, we can select what class of material of section we want to investigate. We have seen the IPE cross-section that are the cross-sections with double T shape, they are double symmetric, but they remind us of a capital I letter. That's why it's called IPE. Okay, I profile basically. With the two flanges, which are smaller than the web. If we untangle IPE, okay, let's stick to the IPE. In this page, in this second table, we can see all the properties. G is the weight, the linear weight, so kilograms over meter. So what is the weight of 1 meter of this beam? The height, obviously, is IPE80. It means that the height is 80 centimeters, 80 millimeters. The B, so the length of the flanges, everything is explained in this small drawing. TW is the thickness of the web here. TF is the thickness of the flange. And R1, R2, R1, R2, the area, and so on. R1 and R2 are just le curve di raccordo, how the radius of curvature of these two parts, but they are basically neglectable. Then we have the area, we have the inertia in the y direction, the bending resistance modulus, and so on, all the other terms. But we have all them listed here, so we don't have to look for in the table. If we select IPE 100, IPE 200, we can see that all the values down here are changing, and we can see that we have all the materials that all the information that are provided in the table. So in this case, let's stick to IPE 200, and we have all the information. Let's say that we want to use an HEA cross-section, HEA 300. So we have to untangle IPE up here. So we do not select IPE, but we select HEA. We update the table, aggiorna tabella. We have that the table changes because now it is plotting us, it is listing only HEA profiles. We can see that the cross-section changes because it reminds of the capital H rotated. Okay? Because the flanges are much wider than before. That's why it's called HEA, because it reminds of a capital H. So we said that we want to use HE300A cross-section. So we select this one. Here we have all the information. We just plot it. And we can see that every time we select a new cross-section, here it is automatically updated. And if we go back to section, here we have the information on section area and inertia that are associated to this HEA 300. Here it is plotting the equivalent rectangular of that cross-section. Useless. Okay, close. Now we have really defined everything. We can solve it. As I said before, we are running just linear static analysis. So there is something that has changed. Here the block notes is selected. It means that we have the results of the analysis. The results of the analysis are clear because three buttons are now colored. The first one is the displacement scale. Okay, this first part of the lecture will be very slow because I have to introduce you to everything and it's all brand new. Then the other examples that we will see are clearly going faster because we will just exploit the software to make some consideration on the structural behavior of different structures. So if we toggle displacement scale, we see this menu. It asks us for a percent scale or an absolute scale. So basically, Sveva, are you sure you run the analysis?
Which part of the analysis?
Which path? Just go on solve linear static and you click it.
Okay, yes, now it works.
Okay. In fact, now you can see that they are in color now, otherwise they are gray. And this block note is selected, otherwise it is like this. Okay, let's run again. So the displacement scale, let's say 10%, I don't know, it's the same. Okay, here we have our deformation, the deformed shape of the beam. Is it what I expected? Yes, because we have that the deformed shape that the beam deforms having a displacement.
Can you repeat this step? Sorry, can you repeat this step?
Yeah, sure. Every time we run an analysis, first thing is plotting the deformation, even if we don't care about the deformation. We just go and look the deformation, and we ask ourselves, we have to be very critical, and we understand if the deformed shape that we find is the same of what we were expecting. Okay, so and
The deformation.
Yeah, and the deformed shape is this one in purple. You have to ask yourself if it is what you think it is, what you think should be, and you care about only on restraints to see if you have set them properly, if you have any displacement that you do not expect in any displacement, in any nodes, and the nodes where you have the load applied. In this case, we have a load applied in node 2. The node is going in the same direction, so it means that it's okay. Then we have node 3, we had a vertical support. So we expected a rotation there, and we expected possibly an horizontal displacement. In this case, no, because we have no horizontal force. And then because the beam is very stiff in its longitudinal direction. But if you find any, and this is also an assumption that we do, that elements are always stiff, meaning infinitely stiff in their longitudinal direction. So we can expect some deformation, but they are very small. And we should not be able to see them from this kind of analysis. Okay. And then in the node 1, we have no possibility of vertical displacement. So in fact, the beam is in the same point where it was undeformed. No horizontal displacement, okay, it is there, and no rotation. In fact, the beam starts horizontal and then starts to rotate. So we have no deformation at all, no displacement at all here. And we are very happy. It means that the structure is what we wanted it to be. Then we can go check an object. We return on displacement scale, we set it equal to 0, and it disappears. Otherwise, we do not understand anything. Then we go on. We can see from this menu the internal forces diagrams. So we can see the bending moment, the axial force, and the shear force. Let's go first on bending moment. That's what we get. This is the true result. in fact, we see that it starts from some value here, and that's what we expected. We expect a bending moment here because we have a clamped in section. Okay, so if the structure cannot rotate, there must be a force that prevents the rotation. And in this case, it is the bending moment. And it is negative because we usually expect it, I said it several times, in the internal points where the, okay, let's go back and plot them all together. More. Okay. There is some very nice consideration we can do about the sign of the bending moment associated to the curvature, because we have always said that bending moment is proportional to the curvature. But a positive bending moment, where with positive we mean that induces tensile stress at the bottom and compression force at the top. As you can see, all the drawings we do when solving a structure, our reference says that the positive bending moment is the one where we have tensile force at the bottom and compression at the top of the structure. In this case, in fact, the bending moment says minus 93.75. We usually draw the bending moment on the side where we have tensile forces. So in this case, it is positive mainly during the span, in the span of the beam. In fact, in the midspan, it is obviously positive, the bending moment. And that's why we have positive bending moment plus 78.13. This positive bending moment is everywhere we have a upward curvature. What do I mean with upward curvature? If we check the curvature of the beam, the purple one, we see that where the bending moment is positive, or where it is drawn at the bottom of the structure, where we have positive tensile stress, from here to here, we have a positive curvature. So it's like the beam is smiling, okay? It's deforming associated to this curvature, a positive curvature upward. Whereas, where the bending moment is negative, this part, we can see that the structure is not smiling, is sad, because the displacement, the curvature is going in the opposite direction. Where the bending moment is negative, is zero, here we have zero curvature. In this point, the beam has no curvature, because it's moving, it's changing from a region where it is negative to a region where it is positive. Obviously, here the curvature is very small, very negligible. In fact, the bending moment is very small. Here, where we have the higher bending moment, we can see that the curvature is higher. In fact, we have that the beam is changing its shape very abruptly. So let's go on the axial force. Obviously, it's zero everywhere. Let's go check the shear force. Shear force, obviously, we have no distributed load, so it is constant piecewise. And it is positive in this first part and negative in the second part of the beam. The jump between the discontinuity between the shear force at the right side and between the left side and the right side of the applied load is equal to 78.75 plus 31 minus 25. It should be minus 31, so minus plus. So the difference between these two values is, if you do the math, 100. 100 is exactly the load of the external load that is applied in this point. So these are all the checks that you should be able to do also when solving a structure working on by hand computation. Okay, all these kind of stuff, once you have drawn the bending moment, the shear force, the axial force, is okay. Now I put my pen on the table, I just watch the drawing and I try to understand if it makes sense. Obviously, since it is all computer based, it makes sense. The point is it what I asked him? Then there is this last option, the pick command, which is very useful and allow us to understand find values of the reaction and of the displacements in any point of the structure. Okay. So for example, in the node 1, in the node 2, in the node 3, and so on. If we go on the node 1 and we look for the displacement, here we have displacement or reactions. In node 1, we have a fully constrained restraint. So, section. So, all the displacement are obviously equal to 0. If we go on node 2, we will find that we have a displacement in the y, in the x direction equal to 0, obviously. A displacement in the y direction equal to 0.0029. So we have 3 millimeters of displacement downwards. And we have also rotation. Okay, we have rotation because the structure is not symmetric. Then if we go on node 3, we have that in the node 3 we have 0 horizontal, 0 vertical displacement, but we have rotation. And it is positive because it's clockwise from here. It depends on what we are looking at. Let's go and check the reactions. In node 1, we have the horizontal reaction Fx is equal to 0. Fy is equal to 68.75 kilonewton, which is the same value of the shear force. So it is the vertical reaction in the node 1. The bending moment in that node is the unknown redundant bending moment that we were investigating when we were doing all this stuff. The x is 3pl/16. If we do the math, and we know that p is equal to 100 kilonewton, L is 5 meters, we compute all the stuff, we find 93.75. Then node 2, here x and y states the position of the node in the plane. Okay. In the node 2, obviously the reactions are equal to 0 because we have no restraint. In the node 3, we see that we have 0 horizontal force. Obviously, we have a roller. Then we have 31.75 vertical reaction, which is again equal to the shear force that we had found. It is the reaction, the vertical reaction in the node 3. And it is obviously this one, where it's not L over X, but X over L. So it is a little bit less than 1/2 of the load, whereas on the first part it is a little bit more than the half of the load. This, how much this a little bit is, depends on the value of the static unknown. And then we have the bending moment, 2.4 e to the minus 15. But we expected 0. Okay, so this is 0. Maybe not all of you will know, but when we see a number with e followed by a number, it means that it is the power. So it is a number, 2.416. Instead of e minus 15, we have to read times 10 to the minus 15. So it is basically 0.00000000200022416. So it is 0. Then this is all the information about the nodes. Finally, you can see the information about the beams. After this, we can have the quarter power of rec. Okay. I think it's wasting enough. We can see the beams. So beam 1. Here we have some schematic that tell us which nodes it is connecting. So it is connecting node 1 and 2, and has a length 2.5 meters. The beam property is the property 1. We can have the ending values of shear force, axial force, and bending moment at the start, at the end of the beam, or the diagrams. These diagrams, if we change this value, I don't know, I want to see what happens at 1 meter. We have this line set at 1 meter. Please remember that the length of this beam is 2.5. And so it tells us not only the minimum and the maximum shear force, axial force is the first one, shear force the second one, bending moment the last one, but it also tells us the value of the shear force in this node, the axial force in this node, the shear force in this node, and the bending moment in this node, so that we can find, for example, the maximum values of bending moment where it is not clear to understand where it is. And then also information on the stresses and if you have something released, but we're not interested in it. And then if we go on the second beam, which is more interesting, we check on the diagrams. Okay, no. Okay, no, we see basically the same stuff. And we can investigate the axial force, the shear force, and the bending moment at any point of the structure. So if you have any question about all this stuff,
Professor, I have a few questions.
yeah, please.
First, you said that when we were drawing the beam, the software understand it it is a whole beam, one holistic beam, if I'm not mistaken. If we don't give it different properties, different yeah. Am I right? So as we have not simple curvature of displacement, it's because of we have different kinds of constraints at the two ends of the beam.
You mean why the curvature is not symmetric?
Symmetric, yeah, symmetric.
Yeah, the reason is that one, because the structure is not symmetric. So
yeah.
the maximum deformation will not be in the midspan.
Okay.
It will be a little bit shifted. So the curvature is not symmetric.
Thanks.
You're welcome. Any other question? Okay, if we have no further questions, we can set a 10 minutes break. Okay, let's say a quarter of hour break. And see you here at 12:15. Okay? Let me. Okay, the meeting, the recording has been resumed. And now let me share the screen. Okay. So we were basically here. Okay, let's just review very. What? I think that there is someone with the microphone on. Now it seems to be everything all right. Okay. Well, okay, let's just review very quickly what we did before. First of all, check the model units so that you know you are actually in control of what you're doing. Then check the geometry nodes, fix the geometry, how to start, how to select, define the geometry. First of all, select all the nodes. You have to put a node everywhere you have some discontinuity in the geometry, or maybe some change of direction of any element. And every time you have some discontinuity in load, so maybe a load that is applied, or the beginning or the end, or elements where you have distributed load applied. And then you define also the elements, just connecting all the nodes. If you forget to connect a node, the program will get crazy and you will be sent out of the software because you are not defining the structure properly. Then we have discussed about the attributes of the nodes, talking about restraints and forces applied. So first of all, we have seen how to check how if the load is the restraints are correct, and then the load applied, how to check the direction of the load applied, simply checking the results of the minimum of the arrow that pops up. Finally, definition of section properties in terms of material and of sections. And then the resolution was quite trivial, the menu solve, linear static, and the investigation of the results can be done in terms of deformation, in terms of internal forces, and in terms of displacement and forces applied locally in the nodes or in the bits. Now, we were talking about before, when I showed you the outline of the lecture, that we would also have investigated the flexibility coefficient. So try to understand what it is, okay? You should already know them. Many of you already are acquainted with them, simply about reviewing the content of the lectures and doing exercises also on your own. Now let's consider this simply supported beam. We have a force applied, a bending moment applied on the first end of the structure, and so the deformation of the beam is as it drawn in blue. We know that the flexibility coefficient of in the node A, in this case, is x times L over 3 iota. Okay, we have seen it basically always. Every time there is an exercise to solve, this flexibility coefficient appears. So we should all know him by memory. but what's the meaning of it? Okay, it's just a series of numbers of letters, one after the other. If we just use the software, and now we can do it, assuming beam is still a structure, so 210 gigapascal Young's modulus, the inertia moment of associated to the IPE80, that is equal to 80.14 centimeters to the power of 4. And okay, sorry, just give me 1 second. Okay. Sorry, guys. Okay, here we go. Okay, assuming a length of 1 meter and a load, no, a bending moment, sorry, of 1 kilonewton per meter applied on the node A. So we can just save it, open a new one. We can go very quick now. The beginning still in the first node 0, 0. The second one in 1, 0, because it was just 1 meter long, very small beam. And create again element. We connect number 1 and number 2. We have to impose the attributes, so the restraints. In the first node, we have an hinge, right? And in the second node, a vertical roller. Then the load attribute node, because it is a concentrated moment applied only on that beam, only on that node. So force moment. In the node 1, we select node 1, and we just say equal to -1. Am I right? Okay. I don't know if it is 1 or -1. Let's go for 1. And we see that it is counterclockwise, so exactly what we wanted. And finally, the properties of the beam. We said that it is immaterial, so material still. And the section is an IPE80. So we go on geometry, profili. IPE80 is the first one that appears. Okay, close. Now, if we try to solve, here we go and find the deformed shape. If we click on pick, in node 1, we find that node 1 has 0 vertical displacement, 0 horizontal displacement. That's what we expect. But we also find a rotation, so 0.001981, 80. And if we substitute all these terms from the analytical expression of the rotation in the node 1, that is the flexibility coefficient, the flexibility coefficient associated to this load condition with this value of the Young modulus, that is the one of the steel, the one that we have defined also in the Telaio. This section that is associated with this Young's modulus, this inertia moment, this length and this moment applied The rotation in the node 1, in the node A, will be this stuff, and substituting the terms, I find 1.98 times 10 to the power of minus 3. So the same number that we have here. Okay? So we have seen that also with the software, we can find the same deformed shape and the same value of deformation, of displacement or rotation in this case. So flexibility coefficient have a really physical meaning. It can be tough to see because we are using Greek letters, and they always appear as a function of several coefficients, but the meaning is just rotation. Okay. Okay, that was just the resolution of the analysis. Now, exercise number 3. A free-hinged arch. So we have two beams which are mutually connected by means of an internal hinge, and they're also connected to the ground with external hinges. So let's check if the structure is statically determined or not. If it is a free-hinged arch, it is always determined. But let's check it again. We have two elements, so 3 plus 3 degrees of freedom, and 2 restraints per each hinge. So 6 degrees of restraint and 6 degrees of freedom. So we can solve the structure using only equilibrium equations. That is very comfortable. Now let's see how should we solve this structure. The resolution is quite simple. It's not that tough, but obviously requires a lot of computation. And since we're talking with structure in the plane, we also need to know the exact position of the points in the structure. And we have a vertical distributed load applied only on the beam AB. Both beam AB and beam BC have horizontal span of 5 meters and vertical height of 2.5 meters, so that the complete diagonal length of each element is 5.6 meters, basically. Now, if we want to solve this structure, the first thing we have to do is, and you know very well, explicit all the external reactions. So horizontal and vertical reactions in the node A, horizontal and vertical reactions in the node C. And and possibly also, since there is basically almost no equation that we can write such as to let appear only one unknown, it is better if we also start splitting the structure in two, and we can distinguish between the forces that these two beams are exchanging one to the other. Obviously, since we have one hinge connecting the two elements, we have no bending moment connecting the two beams, because we have the possibility to have rotation, and if we have possibility to have rotation, we have no bending moment. So the first equation, that I don't want to go into details, the first equation is the moment of all the forces of all the system with respect to node A, so that XA has 0 lever arm, YA has 0 lever arm, XC has 0 lever arm, because they are all passing through node A, whereas node YC has a lever arm equal to 2LX, so 10 meters. This stuff. And then we have also the external load, Q, whose length is, whose force is Q times L, the complete L, and its lever arm is 1/2 of the horizontal span of the beam. So 1/2 of Lx over 2. These two, the sum of these two bending moments of these moments are equal to 0. So this leads into finding the value of Yc, which is 4.2 kilonewton. Then we know one vertical reaction, so we can directly find the value of the other vertical reaction simply applying the vertical equilibrium. So the equilibrium of all the structure of all the forces in the y direction equal to 0. We have Ya, we have Yc, and we know its value now, and we have the external load. All these terms summed up with the right sign are equal to 0. So we find the value of Ya, which is 12.6 kilonewton. So as we expected, Ya is way bigger than Yc. If we had found the other way around, maybe we could go back and check our computation. Then, in order to find the values of Xa and Xc, we have to compute the bending moment of just one beam. In this case, we can use beam BC because we do not have the external load, so the equation will be simpler. And we compute the bending moment, the moment of rotation of all the forces with respect to node B, of all the forces applied on the beam BC, not on all the forces. So theoretically, also the axial force and the shear force that the beam AB exchanges with the beam BC appears. They have their own angles, obviously, because the axial force of the beam AB is longitudinal to beam AB, and the shear force is tangential to it. So we should work with sine and cosine functions, but if we compute the bending moment of all the forces with respect to node B, both the shear force and the axial force of the node AB in the node B have 0 lever arm. So they do not appear in our computation. We only have Yc, and we know Yc, and the lever arm of Yc with respect to B is Lx, so the horizontal span. Whereas we have also Xc, which has lever arm equal to Ly, okay, because it is horizontal. We compute this equation, and we find that the value of Xc is 8.39 kilonewton. Then, now we have found Xc, we can directly find also Xa, simply applying the horizontal equilibrium of all the forces. So we write this stuff, we have only Xa and Xc equal to 0, their sum is equal to 0, and we find the value of Xa. Now, we have done all this stuff and possibly made some mistakes and gone back, found the mistakes. Then we have to compute also the internal forces, so other equations. I don't know, 1 hour of computation. Okay. Instead, we go on Telaio. We have to create the structure. So first of all, geometry. Geometry means elements and nodes. Let's start with the nodes. So the first node is always 0, 0, because it's useful. It's helpful. The second node is in 5, 2.5. Let's see if I did any mistake. No. Here it is, node 1 and node 2. Now let's go again, node. This time we have tin 0. Okay, so we have found node 1, node 2, and node 3. Attribute, no, create element. We connect node 1 to node 2 and node 2 to node 3. Okay. So the geometry is done. Now let's look for imposition of the reactions of the restraint. So the structure is restrained with respect to the word only in 2 points. Okay, in the node 1 and in the node 3. Let's try to attribute, to assign the right restraints node 1 and node 2 and node 3, because we have that the 2 beams have the same restraints, which prevents the displacement but allow rotation. So we free rotation, we only fix x equal to 0, y equal to 0, both of node 1 and node 3. Okay, we have the 2 lines appearing. We are quite right, quite happy. Now, let's go for the load. This time the load is distributed, it's no more concentrated in 1 point. So, you just follow my flow, okay? And try to be critical about it. In this case, the load is an attribute to the beam, not to the node. Distributed load, we select node 1, element 1, and we have that the vertical load was -3 kN/meter in the y direction. Apply. Okay, this is what we expected. Now, the properties of the material. We are dealing with a steel structure, and the profile is for material steel. I'm not doing it slow, but it's quite trivial. Geometry, profili. We'll go look for the profile window, and we want HEA 200. So we unselect IPE, we select HEA cross sections, we update the table, and we select HEA 200 or HA 200A. HE 200A. We see that we have clicked on this profile, and it appears also in the original window. So we can close this, we can close this. We are basically done, and we can run the analysis. Okay, let's start with, okay. Originally we should find this. We go look for the deformed shape, which was the one before. Okay, do you think it is right? Or you are surprised that it is like this? Take your time. Let's go back to, okay, this was the original structure. Do you expect this structure to deform like this? Or not? We didn't define, not, okay. Okay, you jump it to the solution. Thank you. Let's just unselect this. We look for the bending moment. We found the bending moment. Okay, you just told me, someone just told me from here I cannot chat here. Okay,
Sir, I
here
have
in the
a
chat.
question.
Yeah, please go.
How we can remove some constraint from the nodes? It's almost impossible. If we give the
If you
nodes
make a mistake,
if we give the nodes a false constraint, how it is possible to remove it?
you just selected a new one. Okay, let's just change it, attribute node. Assume that I want to put a vertical roller here. Okay, so I want to remove the horizontal one, the horizontal restraint. So I will go on attribute node restraint here. Or I have to delete, or I have to apply. But assume that I want to remove the horizontal restraint here. I select node 1. Okay, you have to go on delete. Use the delete.
Yeah. Thanks.
You're welcome. But now let's just reapply everything. Okay, no, now. Ageda, sorry for my pronounce, said we didn't define node 2. And he may be right. But I was asking you something different. I was asking you, is it what I expected in terms of deformation? Yes or no? If you say we didn't define node 2, I expect that you're not satisfied with the result. And so I want to hear out loud why you're not satisfied. Here I am plotting in purple both the deformation and in red the bending moment.
Should I say it or hello?
No, I didn't understand.
Can you hear me?
Yeah, I can hear.
Okay. So if node 2 is a, I don't know if it's the correct term in English, adjoint.
Yeah.
The moment
a
is
hinge.
to be 0. Sorry?
Yes. The right term is a hinge. It's an internal hinge.
Sorry.
Okay,
All right.
no. Yeah, you're very right. If we have an internal hinge in the node B or node 2 here, we expect to have here 0 bending moment. And if we have 0 bending moment, we know that there is no transmission of bending moment from this part to the other part. Okay, so these two nodes can rotate one with respect to the other. Okay, thank you, Ageda. And I'm sorry for the pronunciation. If I did it wrong. We expect that just this beam deforms. Now here we will have some rotation between the node, the beam 1 and the beam 2. And then the beam 3 is basically undeformed because there is no load applied. Okay. How can we change it? In fact, I told you during the previous exercise that if we just connect more elements, the software will assume they are fixed one with respect to the other. In this case, we have to close to quit the analysis. So we click on the block notes if we want to modify something. Attribute, beam, and release. So we are releasing one or the other end of the beams. Releasing means allowing motion. Okay, so we are releasing internal restraint. And this is what we need. In fact, if we go on, we select the node 1, the beam 1, element 1, which has a start in node 1 and ends in node 2. We want to release the rotation in the node 2. So in the node end, we can decide to release the node start or the node end. We will release the node end. What do we want to fix and what do we want to release? Transversal in direction 1, transversal in direction 1 is the transversal displacement. Transversal. This should be displacement. Okay, displacement 1 is longitudinal to the element. So are we allowing like as if it was a slider? Okay, un pattino o un manicotto in italiano, that they move in the direction longitudinal? No, because we have an internal hinge, so we are fixing it. Are we allowing transversal displacement? No, because it is an hinge, and the hinge says that the same displacement I have on one side has to be equal to the displacement I have on the other side. It's like any book, okay? This is an internal hinge between these two parts of the nodes. So we are fixing it too. The rotation as well has to be released completely, not partial. If we go on partial, you will ask as stiffness, as if it was a spring. But we want to release at all. Apply. And a blue chan circle appears close to the node 2, meaning that we are releasing something in there. Okay? We run again the analysis. Okay, this time what do we find? We find that both the deformed shape is exactly what I expected and what I said before. I have deformation in the node in the beam 1 and no deformation basically on the node 2. There will be a slight deformation for because this point is slightly moving downwards, but we don't care about it, and it's just numerical. It is reasonable, but in our assumptions we just say that the beams show no displacement in their own axis. In this case, we can see a deformation also because the two beams are not vertical, but they are inclined. Okay, also the beam, also the bending moment in red is just present only on this part. And obviously, since we have a distributed load going downwards, the bending moment will be all on the other side, because it is a simply supported beam. And it is parabolic, because if we go and look for the shear force, it will be linear. Okay, so distributed load, distributed transversal load means linear shear force. Linear shear force means that the bending moment is not linear, but it is parabolic. Okay, it is always a polynomial of higher order, the bending moment with respect to the shear force. Then, if we see the axial force, we find something like that. We find that for the first time during this course, we have an axial force in this element because there is a term, a part of the load that is applied in the longitudinal direction in this way and in the other way. And why? Because the beams are not horizontal, but they are inclined. So we have a component of the vertical load that is, we have to consider that the vertical load has two components, one longitudinal and one transversal. The transversal one induces shear force and bending moment, as usual, when we have horizontal beams with vertical load. But the longitudinal component of the load, of the external load, is associated with axial force. That's why the axial force is increasing from a certain level, minus 5.6, to minus 13. Okay. Why minus? Because the reference is positive when inducing tension. In this case, obviously, the beams are compressed, so they are negative. Okay, we just end up in a couple of minutes to have a little break. Sorry. Now, okay, we can just okay. Basically, this example is done. Now I have to ask you a break of 5 minutes, no more, because I have an issue here with a technical issue, and I'll be back in 5 minutes. Let's pause. When I run the solver, it told me that there is a rotation in node 1. Just like that, I couldn't answer. Maybe if if we have time later, we can see it directly, or you can connect to my web page in the afternoon whenever you want, so that you can show me. Because it's not a command, it's not a warning that I can understand the problem. Okay.
Sorry, before you begin, in which days of the week you are available for asking questions and things like that?
Yeah, I said, and it's also, it should be, you should have received an email for the warning.
Wednesday?
Yeah, Wednesday.
Oh,
From
okay.
5 to 6. But if you have, that's just because nobody is asking me help, and I know that it's not so true that you don't have any issues. So if I tell you that I am there, maybe someone will be more inclined in join. Otherwise, you can write me whenever you want, and if I have time, I reply. I know that some other student wrote me, but I was on field all day yesterday, and I returned in Milan like 8 in the evening, so I didn't reply. Sorry. But if you write me for any problem, I will answer you. Maybe not every day, but so we have done this exercise, and if we okay, so just doing just creating the structure very quickly, we can find all the properties that we are interested in solving the structure, neglecting all these computations that may sometimes lead us into error, but they are important in order to check the results. So just to go beyond and to show you that in the slide there is basically everything. This is how you create geometry, node elements, restraints. Restraints, they are attributes of the node because they are punctual. Then the load, in this case, it is a distributed load, so it is no longer an attribute of nodes, but it is an attribute of the beam. And here we have the window that appears where you can specify the direction and intensity of the load. Please also remind that there is toggled this menu Q start equal to Q end. If you untoggle it, you are saying that the load is not to be constant, but it is distributed and can vary with a specific law. And it will tell you the Q at the beginning and the Q at the start and the Q and at an end. So it will appear here. There will appear here 2 more windows, 2 more boxes, where you can select the final value of the X load and the final value of the Y load. Easy peasy. Then the section properties, the definition of the material and of the section. Here the results with the vending moment. That's something I didn't show you. Or maybe yes. Yes, I showed you in another exercise. If we look for the reactions in the node 2, in the node 1, obviously. Okay, in the node 1, for example, we can find the reactions 8 point something, 12 point something, and they are the same results that we found working with any computation. And then we find also the vending moment, which is a very long number, and you can see at the end it's still E minus 16. So it is 0. If you find E16 without the minus, obviously it means that all the numbers before are not multiplied times 10 to the power of minus 16, but if it was E16, it will be times 10 to the power of 16. So it will be a very large number. So don't think that if you see E, it is 0. It depends on the exponent. It is the exponential notation. So here I also plot the problem of internal release and release. And here we have the exact result. Okay, next exercise, plane frame. Well, basically, what do we have? We have that a plane frame with 2 columns and 1 beam. I'm sorry, I may consider also to have another very, very short interaction of the lecture because my laptop is stopped working, so there is technical assistance that is taking care of it. Now, and as soon as he will have done, I will have to go and recover it. So, in this case, we have a plane frame with a hinge here and a vertical support here. So basically we have 3 degrees of freedom and 2 plus 1, 3 degrees of restraint. So it is statically determined. Okay, let's go to it. We create a new one, again, before the geometry. So first the nodes, the first is 0, 0, then we go upward. We have weight, height equal to 3, so it is 0, 3. Apply. Here we have the second node. Then 5 is the span. So we have the third node, and then we go back to x equal to 0, x equal to 5, y equal to 0. So we have the base of the second column. Then we create the elements. Create element. From 1 to 2 is the first column. From 4 to 3 is the second column. Then we increase the number of the property, and we select node 2 and node 3. So here we have selected a new beam property. This is for a different cross section, obviously. And in this case, it is the cross-section of the beam. You can see that it is highlighted in yellow. So attribute restraint. Here we have a hinged section at the base of the first column. So x and y displacement are fixed, equal to 0, whereas the vertical support in the second one. Okay. Now we can we have to impose the load. The load was equal to something. Okay, I didn't write how much it was. So beam distributed load minus 10, minus 3 kilonewton over meter, which is let's say a standard load for residential loads. It's not so weird. This is fine. All the elements do not have any internal hinge. That's right. We have to impose the properties. So let's go first on beam property 1. Material, let's stick to the steel. Geometry. We go on Profili, and we can see that HEA, the columns have cross-section HEA 260. We have selected it. Okay. Then we have material and property. If we go on the second property, we still take steel, but the geometry, it will be IPE 220. Okay, we have selected the ones we wanted. If we go beyond, if we go back to check, the first one is still HEA 260, and the second one is IPE 220. Okay, we can run the solution linear stop, linear step. That's what we find. Okay, we expect something like that, but okay. We expect it because we have a this beam that tends to bend under the load. Okay, if it bends, it means that in the first node and in the second node we will have a rotation. Okay, this rotation means that we are transferring some curvature, but not the beam 1 and the beam 2. Since we have a fixed section here, they have to share the same angle, so it must be still 90 degrees. So if we have an horizontal deformation in the beam, we expect also a vertical deformation at the beginning of the column. Okay, and so we can simply connect the beam, the column, from this point to this point, because we know that the first the base will not move because we have an hinged section, whereas the second one we have here a rotation for the same reason, because we have an horizontal deformation, so a horizontal rotation of the beam, so we have a vertical rotation of the column, because this angle has to be the same. It doesn't mean that it has to be 90%, 90 degrees vertical horizontal. It means that the two beams can rotate, can display, can go around the world, display, but they have to share the same angle, which is 90 degrees. But in this case, this point has 0 allowed vertical displacement, but the horizontal displacement is free. So this moves from this point to this point. In fact, we have a vertical support. Okay, so vertical rollers, basically, it means that it can move. And in fact, in this case, it moves. So this is what we expected. If we go on the bending moment, we can see that basically the bending moment is only when the load is applied. Here we have no bending moment, and here we have no bending moment. Why? Because if we had any transfers, any transmission of bending moment from this element to this other element, then if we have no applied load, so this bending moment will transfer here, and but here we have a how to say it, an hinge. So if we cut the structure here and we make the equilibrium of rotation with respect to this point, we find that the bending moment in this node has to be equal to 0. It cannot be any else. Same for the other part. Shear force, here we have the plot. Please remember, we have a linear shear force because we have a distributed load. If we have a linear shear force, in this case, it crosses 0. When the shear force crosses 0, we have the maximum or the minimum bending moment. And in fact, the maximum bending moment is here, right in correspondence of the 0 shear force. That's why when we want to find the maximum bending moment, we have to find 0, the place where we have 0 shear force, which is a simple equation solved. And then the axial force. Obviously, there is no axial force in the beam because there is no longitudinal load applied to the beam, but we have a longitudinal force applied that is transferred from the beam to the columns, and it is longitudinal in the columns. So we have 1/2 of the load and 1/2 of the load applied here. Okay, that's all. No, something nice. If we go on peak, still I didn't show this. Diagrams of the shear of the internal forces. If we go on the beam number 3, if we want to know the maximum value of the bending moment, we can just say, okay, I want to find the section where there is maximum bending moment. But now we know that it is 2.5. Okay, but assume that we don't know. So we look for 1 and we have 6 kilonewton meters. We have to increase, so we say 2, 9, which is higher than before. But we see that the maximum is yet to come. So we go on. But if we go on 3, it's 2 beyond, and we find the same value of the bending moment. So if we go on the 2.3, we will find 9.3. 2.4, 9.36, 9.5, 3, 9.3675, and then back to 36. So in this case, we can use these comments also to find value of the maximum bending moment, or to be sure of it once we have found with the end computation. Now, what happens if the beam, so the property 2, is no longer an IPE 220, but becomes an IPE 600? So if I increase the load no, the stiffness of only the beam, what will happen in your opinion? Do the axial forces or the internal forces or the action change? Come on, yes, no? I don't get the answer. I don't get the answer. No, the question. I mean, did you understand what I'm asking you? Is anyone alive? No, the actions won't change. Thank you. Yes, because as I said before, not because I said it, as I said before, in the statically determined structures, the distribution of forces do not depend on the distribution of stiffness. In fact, if we try to solve, we will find the exact same values of before. Okay. Obviously, there will be some difference in the displacement. In this case, the rotation at the beginning, node 1, is 8 times 10 to the power of minus 5. It will be different if we change didn't. Double check. No, okay. I should check the displacement or something. The point is, okay, if we change the this, okay, if we change the restraints, and in this case we assume that here there is a clamped in section, and here we have, sorry guys, just 1 second, I don't know what's happening. Okay, I'm back. So in this case, I was changing the restraints. So in this case, we have a hinge in the node 4 and a and the clamping in section in the node 1. Okay. We just may want to divide. Okay, in this case, I have subdivided the beam into 2 beams. Nothing has changed, but we have 1 node more, the node in 5. And we can exploit this node in order to find the deformation. Okay. So before it was IPH 120. Okay, let's just solve it. This is what we have. So we have 2 columns with this time we have a presence of bending moment also in the columns. Okay, because we are restraining it. Yeah, sure. Tools, subdivide. You select the beam you want to subdivide, and you select the number of divisions you want to perform. Now that beam will be gray forever. And now, okay, we can see that the maximum bending moment here is 7.9 kilonewton times meters, whereas the minimum bending moment will be 1.6 negative kilonewton meters. We have a bending moment here because we can expect it, but the bending moment in the hinge is equal to 0. And if we go on the node 5, the displacement in the node 5 is the vertical one 0.0001. So it's 0.1 kilonewton meter, 0.1 millimeter. Sorry. .15. Now we do what we did before. We take it to IPE 600. We have to do this. Now, if I solve, will something change or not? In your opinion? We have seen that before, nothing changed, even if we changed the properties of only the beam. Now I showed it, I have changed it again, and I'm asking if it will change anything in the actions. Yes, no? Any guess? Okay, I will solve it anyway. Maybe change it to a little. Let's degree. 220 to 100. Okay, it changed, but changed it too little. I didn't have to change in that way, but the other way, because the beam is already stiffer than is already taking a great part of the axial force. So, in this case, what do we have? We have something that we cannot see completely. Okay. Okay, we have that the maximum bending moment here is much less than before. Before it was 7 point something, and now it is 3 point something. Why? Because in the previous case, it was as if we had only one beam on 2 vertical supports. Okay. In this case, it is changing the structure. The beam is more flexible now, and so the deformation of the columns come into play. So have a role. So in this case, we can have that we have a more important transfer of internal forces from the beam to the columns. Okay. And if we pick the node 5, we can see that the vertical displacement here this time is almost 3 centimeters. Before it was 1.1, 1.2. Millimeters. So if we vary in a statically redundant structure, if we vary the distribution of stiffness, we have that not only the deformations will vary, but also the distribution of forces. And let's remove for a moment plot. Let's check only the displacement. We can see that not only the beam is deforming, but also the columns a little bit. Even though theoretically they're not loaded. Okay. So let's go back to the presentation. So again, how to create the geometry. With different geometries, we have to change the number of properties of the element. We have to do this way. Here the load I had assumed -10. So the result will be a little different, but in my case it was I used 3 kilonewton times kilonewton over meter. These are the first guess. Then I changed the load, and so what happened? Obviously, in a statically, I don't know if you can see from here, if you have a load of 20 kilonewton over meter, the maximum bending moment associated will be 62.5. If the load is -10, the maximum bending moment will be 31.25. If you double the load, also the internal forces, all the displacement will double if we are in a static elastic computation. Okay, everything here is doubled from what we see before. Okay, now space time for the last exercise, the multi-span beam. This will be very important for your homework because possibly you'll be asked to solve some structures like this. In this case, we have a vertical hinge which supports the beginning, the starting of the first beam. Then the beam is continuous over other 3 vertical supports. In this case, it is a highly redundant structure because we have these 2 elements that are not necessary, basically, let's say. It could resist the structure only using these two supports, okay? Because it is statically determined. The presence of these other supports make the structure much more stiff, obviously, but so reduces the deformations. So in this case, assume that in a common case, you would have only have one supported beam with hinged section in node A and vertical support in node D. The deformation associated will be this one with a very high deformation in the midspan. But if you put the internal supports, the deformation will be quite different and the maximum displacement will be much less. We cannot solve the structure only with equilibrium equation, so I will not do the comparison between the computation and what the software tells me. But we can see just how it works. So create, first of all, we have to define geometry. Now we will have enough of it. The first node in 0, 0. The second node, we can assume we will obtain different numbers from what I got in the slides, because I'm changing a little bit the dimensions. Obviously, when you deal with a structure like this, it can be, usually you find that kind of structures when you are crossing a highway, because all the bridges that you see that are crossing highways have these static have this static behavior. So a continuous beam. Sometimes these beams are much more flexible than the central one, in order to avoid vertical reactions upward in nodes A and B. And the beams and distance of the lateral spans should be around 70%, no more than 70% of the central one. Okay? In order to make them flexible enough. So the node 2 can be at 15 meters from the first one. Okay, no, let's say 10 meters. Changing it. Makes more sense. Then the central span is 25 meters. 35 get to the next point. And 45 meters, adding the other 10 meters at the last span. Then we can create the element. Node 1 and node 2, node 2 and node 3, node 3 and node 4. We have to impose the restraints, attribute, node, restraint. The first one was a hinge, so we just fix vertical and horizontal displacement. All the others are vertical supports, so we prevent only vertical displacement. So y displacement is equal to 0. Apply. We have two lines in node 1 and only vertical lines in node 2, 3, and 4. Now the loads. We can assume that in the midspan there could be higher load. This is for all a series of reasons that we will explain in the next lectures. Because according to the distribution of the loads, we find, I mean, if we want to design this continuous beam with respect to the maximum bending moment in the midspan, we should know that if we load the first span more than the others, we will find higher bending moments here. rather than if we load uniformly all the bits. So if we have the possibility to load 20 kilonewton over meter in the midspan and only 3 kilonewton of meters the lateral spans, we will find the maximum bending moment in the span 2, 3 that is much higher than the bending moment that we would find if we load 20 kilonewton meters, also the lateral ones. So it is worse for the structure when, for the structure in this pen, when there is only, all the load is applied only in the midspan. When there is a load applied also here and here, the excitation of this span is inferior. And with this software, you can check it. This is everything related to the combination of the load cases. Okay. We need only to define the properties. So again, still geometry, profili. Let's go for an IEA 500. A very tough guy. Close. It seems we have everything. We can solve the structure, linear static. Oh, before doing it, we can subdivide this element. So tools, subdivide this one into 2, so that we have the node 5, and we can use this node for finding the displacement in the midspan. Okay, and also the bending moment, shear force, axial force are explicited at any node. So if we have the node 5 and we run it, okay, here we have the deformed shape, and it is what we expect it to be. We have that node 1 does not have any vertical or horizontal displacement. Node 2 has no vertical displacement, has a rotation. Okay, but the rotation is continuous, so we don't have any difference of rotation between the node 1, the element 1, and the element 2. Then here it is continuous. We have our concavity. Here we have positive bending moment, and here we will have negative bending moment. We already know that. If we look at how the concavity goes, we know that because we have already discussed it. So negative bending moment from here to almost here, and from here to almost here. Then if we plot also the bending moment, we check it. In fact, the bending moment is minus 830 here, then goes 0 here. It is positive in the midspan of the central one, and then it is negative. And it is symmetric, obviously. The maximum bending moment is in the midspan 732 kilonewton per meters. Okay. We can go on picking. In the node 5, we have the displacement, and in this case, we find the displacement in the node 1, 0.2 meters. So it means that with this geometry, under this load condition, this point will go downwards of 20 centimeters. So quite a dimension, like this, with a span of 25 meters. Then we can also plot the shear force in order to make some comments. Again, the 0 position of the shear identifies the section where we have positive, maximum or negative or minimum bending moment. In this case, maximum. So we don't have anything else more to say. We can close. Before closing it, let's just resume everything we did. So we create the geometry. In this case, I started with the internal point, but as you see, I have also been able to create it post-process. The restraints, the loads, the beam properties.
Sorry, can you explain the beam properties? Not the properties. When we are creating beam and we create with different property, for example, one beam with property number 1 and the other property number 2. What's the meaning of that?
Yeah, sure. If we go back. Okay, let's say that we want to create. No, okay, sometimes you will see if you drive that in a highway, the central span has a higher width. Okay. In fact, this is the most flexible part where you want the minimum deformation because it is the longest, basically. So how to recreate it? If you want to create everything from scratch, let's create another case. Let's say that we want to create. So everything is not on x equal to, no, the first point is in 0, 0, and we have it. Then we have the first span of 10 meters. Then we have the central span, which is 25 meters. So 35. Then the last span, another 10 meters, 45. Okay. Then we have also the columns. So below node 1, it was 0. Let's say columns of -5 meters. We have created this one. The second point was here. So we create the base of the column below node 2, below node 3, 35 minus 5, and 45 minus 5, the base of the last abutment. If we want to create the element of the central span, this is it. Then we want to create the element of the lateral spans, which can be thinner. Before adding the other element, we have just to change the number of property by selecting this arrow in property. We have property number 2. We go on selecting the nodes that have to be connected by the next element, and we can see that this element is in a different color. Again, now the columns, obviously the columns will be different again. We can say that all the columns are equal, and this time we have green color. Okay, so we have 3 different cases for geometry. We go on, we put the attributes, we put everything. Let's go to the property. The property here, we'll have a window, and we can navigate the window.
Sorry.
Yeah.
So like the beams are different, like the first one and the second one, because the one with the bigger span is like stiffer, right? It's like
Yep.
thicker.
Yeah.
Okay.
That's the reason. You're welcome. And then if you just navigate here, you can define the materials and the sections of all the properties that you have defined. Is that clear?
Yeah, for me it's clear. Maybe for the other.
Yes, Professor.
Okay.
Thanks.
So I'd say, okay, no, please. Do you have any other question? Otherwise, the lecture is done, and you are free to go.
Thank you, Professor. See you.
Thank you, guys. Have a nice weekend. Please remember that next Wednesday I will be online from 5 to 6 in the afternoon. If you
Okay.
want to
See you.
solve any problem, if you want to do something more because you feel that you are losing time, or if you didn't understand something and you are, I don't know, shy, you don't want to ask in front of everybody, you just come to me and we can just to try to fix everything, okay?
Thank you, Professor. I have one last
Okay,
question,
thank
if
you.
possible. Will we get our corrections of the exercises back, and will there
Quite
be an evaluation? Thank you.
Yeah, quite soon I am actually correcting them. I still haven't had time to do it.
Yes, clear. Thank you.
You're welcome.
Professor, at what time can we have the review with you, like on Wednesday?
No, I didn't get the answer. I did the question.
At what time? At what time are you like available for the review on Wednesdays?
From 5 to 6.
Okay, from 5 to 6. Thank you.
If it is a problem for the timetable, please tell me. We can meet at any time. It's just to encourage you coming.
Okay.
It's
No, for me
nothing
it's
big.
fine. Thank you.
You're welcome. Okay, guys. If there is no more, left the day. I will stop the recording.